Hello everyone, my name is Yuri Katz from the University of Haifa, and today I would like to lead you through our design and development process of a Lagrangian float. This is a short presentation, so we'll briefly go over the key aspects of the design and development process, finishing with the testing procedures, and we'll begin with what was our goal and why we undertook this project in the first place. What led to the inception of this project is that a physical oceanographer that our lab collaborates with on occasion approached the laboratory director saying that she's seeing a lot of research coming out on internal waves. While she isn't aware of any data on internal waves in our region, which is the Eastern Mediterranean. Furthermore, she doesn't really have any equipment to investigate internal waves. So it was decided to develop an in-house Lagrangian float to serve as an oceanographic platform for the detection and investigation of internal waves in coastal waters. I'll briefly go over the key aspects of the design and development of the vehicle. Vehicle features and capabilities. It was decided upon a depth rating of 300 meters, which is the depth of the local shelf break, because it was concluded that internal waves would be predominant in this depth range. We wanted the vehicle to be as Lagrangian as possible, so it was decided to equalize compressibility of the vehicle to that of the average of the water column. Mission duration was set to 24 hours, because we operate close to the shoreline and cannot let the vehicle roam freely for more than that. Onboard sensors include pressure, temperature, and IMU, sonar altimeter, and hydrophone. The propulsion system needs to be as silent as possible in order to not interfere with the acoustic equipment. An emergency drop weight was deemed necessary in order to increase survivability of the vehicle. Long and short range comm beacons and strobe is used for localization. And we wanted the vehicle to be man-portable and deployable from a small boat in order to lower costs of deployment and increase flexibility. A dynamic model was deemed a necessary part of this project. For the equation of motion to base the dynamic model upon, we used the equation suggested by Voorhees and later on by Goodman and Levine. As you can see, it is an equation in the form of a harmonic oscillator, specifically base excitation dynamic model. The left-hand side is identical to the mechanical spring dampener model. The right-hand side is a bit different. It's the forcing. Omega 0 is the neutral frequency of the system. Omega 1 is a coefficient originating from diabatic processes, and sigma is a coefficient of energy dissipation mechanisms. The dynamic model was constructed using the MATLAB simulating environment. Here you can see a sample simulation in which the float is controlled by an augmented PID controller. The top graph shows the float depth, the second from the top, the float vertical velocity, the third, the volume of the bladder in cubic centimeters, and the last one, the voltage and percentages of the battery voltage. Here the float was released from the surface with an initial bladder volume of 50 cubic centimeters. The set point was 60 dBars, and the volume of the bladder that would bring the float to equilibrium at the required depth is 27 cubic centimeters. So you can see that immediately the controller lowers the bladder volume to 0. The float reaches the required depth after approximately 760 seconds and begins oscillations of approximately 2.5 meters. You can see that at the end of the run, the bladder volume oscillates between 12 and 36 cc's compared to the 27 required to reach equilibrium at the set point depth. The general arrangement of the float. Here on the left you can see a CAD model section of the entire vehicle. On the right you can see a photograph of the bottom end cap assembly. So this is the bottom end cap. This is where the bladder sits. This is a skirt that holds the drop weight mechanism and the altimeter. This is the main battery. It envelops the shutoff valve. This is the hydropneumatic accumulator. The electronics is situated on the top. For stability, everything that is heavy is situated on the bottom, as close to the bottom end cap as possible. Here you can see the hydrophone, the top end cap sensors. The GPS iridium is in this enclosure on the top, and this is the RF strobe beacon. The float hull had two main requirements. We needed a depth rating of 300 meters with a factor of safety of 3, and we wanted a compressibility of 4.2 times 10 in the power of -5 with the units of 1 over bar. From the beginning, the construction material was set to aluminum 6061 T6, and the design began with a simple cylinder hull. Quite quickly we realized that the hull is becoming too heavy to withstand those two requirements, and we switched to a rib stiffened design. Here in the table you can see the final dimensions of the design. The hull mass is 7.6 kilograms and the volume is 17.6. We have an internal diameter of 150 millimeters and an external length of approximately 860 millimeters. So the strength rating was achieved first, and some further tuning was required to achieve the compressibility requirement. The variable buoyancy engine. Here on the left you can see a CAD model of the entire variable buoyancy engine assembled on the bottom end cap. Here is the actual assembly in our lab, and this is the miniature gear pump that actuates the variable buoyancy engine. Since we intend to operate in coastal waters where sand and other particulates are abundant, we decided to use a closed system, which is a bladder and internal reservoir. As I mentioned, this is actuated by this commercial gear pump. The gear pump is housed in this hydropneumatic accumulator. The pump is submerged within dielectric oil. Here we have a plunger that separates the oil from pressurized nitrogen. For full submergence to 300 meters, this would be the nitrogen would be at 20 bar maximum pressure. So the pump is actuated. It pumps the oil through the tubing, through the shutoff valve. Here we have some sensors to identify ingress of water in case the bladder is ruptured. And the pump fills the bladder, lowering the density of the entire float. At depth, the plunger is at its utmost position. The nitrogen is at its highest pressure of 20 bars, and so the difference on the pump between the 30 bars outside and 20 bars inside is only 10 bars differential pressure, which both helps the power economy and lowers the noise emitted by the pump. The sensors. So we try to use low-cost sensors as much as possible. Here you can see a temperature, pressure, and altimeter, all by Blue Robotics. This is the top end cap. You can see here that we have two temperature sensors, one is hidden here. We have two pressure sensors, and we have an identical assembly on the bottom end cap. This allows us to calculate the pressure and temperature values at the geometric center of the float. It also lowers the measurement error. To further lower the measurement error, we use a 5-point moving average. So we average 5 consecutive measurements per each sensor, per 2 sensors. So we use 10 measurements, and the measurement error is lowered by a factor of square root of 10. This sonar altimeter is currently used to avoid grounding and collision with the ground. And the hydrophone is used to constantly monitor and record ambient sound and to allow reception of commands from the surface. The drop weight mechanism. Here on the left, you can see the photograph of the actual drop weight with the bottom assembly and the bladder. Here on the right, you can see the CAD model of the drop weight mechanism. It is reversed for clarity. It is also the enclosure of the drop weight is transparent from clarity. It's built from of aluminum as well. The whole concept is based on magnetic coupling. Here you can see a bracket that holds the drop weight. Here is a stainless steel pin with magnets embedded inside it. Here inside the transparent enclosure, we have a motor, a drive bolt, and a slider. Within the slider, we have embedded magnets as well. Once a command is given, the motor turns the drive bolt. The slider moves to the left. The alignment between the two magnets from inside and outside is broken. And once they are misaligned, the weight of the drop weight is sufficient to release drop weight, and the vehicle rises to the surface. Briefly on the testing and trials we underwent. The float experimentation began with tabletop tests. This included extensive testing of the miniature gear pump in different scenarios, as well as dry runs of the float algorithms. All of the float enclosures, and this includes the main float hull, the small enclosure that holds the iridium GPS antennas, and the small enclosure that houses the drop weight mechanism, were checked in the pressure chamber. Here on the left, you can see our department pool. So the float underwent first initial wet tests in the department pool. And finally, the sea trial, as you can see the photos here on the left and on the right. The sea trial was conducted in the Gulf of Haifa. For the initial sea trial, the float was to undergo 3 deployments to different depths at the Bay of Haifa. Here you can see the results of the initial deployment. On the top graph, you can see the average pressure reading from the 4 external pressure sensors. On the bottom graph, you can see the bladder volume in cc's. The 2 photographs taken by the divers that accompanied the float on the first deployment, because we were afraid to lose it. The set point was set to 10 decibars. You can see here that the initial depth is 0.4 decibars, which is approximately 40 centimeters, which is the depth of the geometric center of the float when the bladder is full. Here you can see that the initial bladder volume is approximately 650 cc's. So immediately the controller empties the bladder to a minimum value set to approximately 35 cc's for safety reasons. The float begins to submerge. Here we can see a very dominant differential branch of the PID controller, making an unnecessary correction upwards. Eventually we can see the float stabilizing at approximately 9.1, 9.2 decibars, making oscillations of approximately 40 centimeters. After the preset time, the float emerges at the surface, performs an iridium transmission, and that was this deployment. So we're at the end of my presentation, and I would just like to acknowledge and thank the Maurice Heder Foundation and the Israeli Ministry of Science and Technology for their support of this project, as well as the whole lab staff for their help. And thank you very much. I hope you enjoyed it.